Good morning, everyone. Now we move on to the last topic of the unit Formalism of quantum mechanics, that is the momentum representation. I think I should begin with the representing wave function. Okay, so we have been analyzing various quantum mechanical systems or using our wave function in terms of x and t. What does it mean? We are using a wave function which is a function of space coordinates, that is x, y, z. For that we usually represent the total volume. In general we use the notation r, or in 3 dimensions we have r, or in 1 dimension we will be using one of these x, y or z, and also time. So this is called coordinate representation or position representation. Representation over a space, coordinate space, or a position space, or position representation. Okay. So in position representation we have the usual wave function, which is a function of either x, y, z, or in 3 dimensions we have r and time. So space, coordinates and time. What if we have a wave function in terms of momentum and time? So when I say momentum coordinates, it can be px, py, pz, or it can be in 1 dimension or 3 dimensions, and time. So if we have such a wave function in terms of momentum coordinates and time, then we call it a momentum representation or a momentum space. So for distinguishing the functions, instead of psi we can use a different notation, that is phi. So why do we have a momentum space wave function? The only answer, or the simplest answer to that question is to ease our mathematical analysis. Sometimes if we represent the wave function in terms of momentum coordinates, it will be easy for our calculation. So in order to avoid complex calculations, we can either use a momentum representation or a coordinate representation. So if we take an example of various operators, suppose we have the position representation, position space wave function psi, which is a function of x, y, z and t. So for simplicity, let me use only the value x, that is 1 dimension. Okay, so we have the position operator represented as x or simply x, and momentum operator is represented as a p cap, or that is minus I h cut del, or del x, or let me write it minus I h cut dou by dou x, because it is 1 dimension. When we move on to momentum space, in momentum space we have the wave function phi. Again I am going to simplify it by using only 1 dimensional coordinates px and t. So when we change to momentum space, our position coordinate will be, position operator will be a different one. Momentum operator can be written as a px itself. Like we use position operator x in position space, we have momentum operator in momentum space represented as px itself, because we are dealing with momentum space. So when we go for position operator, we should have a different notation, like we represent momentum in position space. So our position operator turns out to be plus I h cut dou by dou p. We can check the analogy between these two things. So position operator in position space is represented as x itself, but momentum in momentum space is represented as momentum px itself. And when we go for position operator in momentum space, we need a different notation, and momentum operator in position space also we need a different notation. So this is how operators get changed when we move on to another coordinate representation. Here we have momentum representation. So we will calculate the probability and expectation values of position and momentum and check how it varies in a different representation. Okay, let us now begin with calculation of probability density. Before that, we use Fourier analysis to have a mathematical expression for the wave function psi of xt in terms of wave vector k. Because if we represent wave function psi of xt in terms of k, it is easy for us to move from position space to momentum space easily using this expression. So for that we are using Fourier analysis and representing wave function psi of x comma t as a Fourier transform of wave vector k. That is a different function phi of k t. Phi is a function of wave vector k and time. So this factor, as you are familiar, this is the constant part, and this is the function to which we are changing, that is the function including wave vector, and this is the exponential part. As you are familiar with the Fourier transform integrals, this is one of such representation for wave function. So it maintains the usual form, so it is not confusing, I believe. So if we have a wave function psi of x comma t, then you can obtain phi of kt by taking the inverse Fourier transform. That is also familiar to you. So that is just by taking the complex conjugate or of the exponential, you can just rewrite the inverse Fourier transform from the same expression. So we have phi of k comma t is equal to the same coefficient goes with and the integral as it is, but the left hand side function comes within the integral psi of x comma t, and exponential should take the complex conjugate of the given function, and the integral should be according to the variable should be according to the function. Here we have phi of k, so we have integral over dk. Here we have x, so it should be integral over dx. So we are just trying to transform to the momentum space. For that we have to use this equation. So how you get this equation? this is from the momentum value from de Broglie relation. We have a P is equal to h by lambda multiplying 2 pi and dividing by 2 pi. We have a 2 pi by lambda is k, that is a wave vector. K is 2 pi by lambda and h by 2 pi is h cut. So you have P is equal to h cut k. So for moving from one variable to the other, we have to find the dp value. Dp, k is a constant, sorry, h cut is a constant. So h cut into dk. So to move from dk to dp, we have dk is equal to dp by h cut. Okay. So let us change it. Psi of x comma t is equal to 1 by square root of 2 pi integral, I'll write it here, dk is equal to dp by h cut. Okay. So integral minus infinity to plus infinity, phi of k comma t. Yeah, we will move this one using a constant after applying this value of dk. E raised to I, instead of k we have p by h cut into x. Dk is dp by h cut. Okay, I'll take this h cut and write it as 1 by 2 pi h cut. 1 square root of h cut is added with the phi of k comma t, so that it is defined as phi of p comma t. Okay, so the remaining is written like e raised to I p x by h cut dp. Okay, so I'll rewrite it here. This is equal to psi of x comma t is equal to, yeah, the square root should be rewritten using h cut. Then this is written as phi of p comma t. Then this is written as p by h cut, and this is dp. Okay. Now the inverse can be written as phi of p comma t. Here the square root of 2 pi h cut, psi of x comma t, exponential minus ipx by h cut dx. So yeah, I'll rub this. So we have moved from the k space to p space, or wave vector k to momentum space p. So we have the momentum space wave function phi of p comma t. Okay, let us now find the probability. How do we find the probability? It is integral psi star psi dx. Psi is a function of x and t. Here also x and t. So since we are moving from position space to momentum space, we will begin with position space. So we will be giving the value of psi star and psi from this equation. Okay, so this is integral. Yeah, I'll write the constant 1 by, actually it is 2 times psi, so it is 2 pi h cut we have one integral over x, so it is integral dx, then integral phi of p comma t exponential we have a psi star, so it is minus I exponential minus I p x by h cut dp. Then another more integral we have integral psi of x comma t, so it is integral, will make it make p a variable because we have two integrals, so I'll be writing it as a p prime t. That the only purpose is to make it a variable, so ultimately it is momentum itself. So phi p prime t exponential I p prime x by h cut dp prime. So this is our probability value. Now we'll analyze which integral is to be evaluated first. So we'll take the integral over x. So we have functions of x, exponential, both the exponentials and the integral dx we have. So we'll evaluate it. So this is, let me write the left hand side as well, integral psi star psi dx is equal to, I will keep the constant here 1 by 2 pi h cut, and integral, these two integrals, phi of p comma t exponential minus I p x by h cut dp, then integral, I should write it phi star, sorry, I have taken the complex conjugate here, so it is a phi star. Already we have given the conjugate of exponential. Okay, integral phi p prime, that is a variable, e raised to I p x by h cut, sorry, p prime dp prime into the integral over x. I forgot one thing. We have to take this exponential to the integral over x, so I'll write this one to this side, dp, and phi of p prime t dp prime, integral e raised to minus I p x by h cut into this one dx. Yes. So we'll perform this integral.